So with that, I would like to hand over the mic to Jay Powell, who again is going to be talking here at Analytical Answers today about polymer analysis and the ways in which it can solve a variety of material science questions. Jay, would you like to take it from there?
Well, thank you very much, Christina, and thank you everybody for attending today. I'd just like to do a little correction on Christina's wonderful introduction of me there. One minor correction is I've never actually done a full Ironman triathlon. I've only done half Ironman distance to date so far, but perhaps someday. Doing a full Ironman takes a lot of commitment and a lot of time. I'd like to spend a lot more time here at Analytical Answers too, doing various analysis. So as you see on the screen there, what we're going to be talking about today is various analysis of biomaterials, composites, encapsulants, adhesives, general polymer analysis. The main technique we use, main technique we use is infrared spectroscopy. And infrared spectroscopy, unlike most of the measurements we do here at Analytical Answers, is a light absorption measurement. What we're actually measuring is energy that's being soaked up or absorbed by the sample in the range of about 2.5 micron to 25 micron. We actually work in units of wave number, so 2.5 micron corresponding to 4,000 wave number, 25 micron at the other end corresponding to 400 wave number. The basic mechanism of light absorption shown here on the screen. Light propagates via a pair of perpendicular oscillating electric and magnetic fields. The oscillating electric field can interact with the bond and atoms bonded together in a molecule such that that bond is periodically either stretched apart or compressed together. That molecular vibration increases at the right frequency of light. That increase in vibrational energy in the molecule corresponds then to a decrease in the light intensity coming through the sample. So what we measure then is a spectrum measuring the amount of light absorbed as a function of wavelength, and we can use that for both identification of what material or materials we have present and for quantitation, how much of a particular component is present. Now I will say one of the major strengths of infrared spectroscopy is that every organic compound has a unique infrared signature. And one of the greatest challenges of infrared spectroscopy is that every organic compound has a unique infrared signature. What that means is if we're trying to quantify the amount of component A in a matrix of component B, we need to have a series of standards of A in B, because component A will also interact with the matrix and change the spectroscopy, spectral absorption patterns somewhat. This is why that infrared spectroscopy is not as quantitative immediately off the bat as other techniques we do here, such as EDS spectroscopy. But the technique we do here is actually called FTIR spectroscopy. Sometimes people will ask, what's the difference between infrared and FTIR? Well, infrared spectroscopy is a general field that we're applying here. FTIR spectroscopy describes the instrumentation and data processing technique for doing infrared spectroscopy. The main component for doing FTIR spectroscopy or FTIR analysis is the Michelson interferometer, which is a component shown up here. One of the jokes in the FTIR instrumentation field is that FTIR is all done with mirrors. We have an interferometer consisting of a beam splitter, a fixed mirror, a moving mirror. As that mirror moves at a constant velocity, all the wavelengths that come through the interferometer are all modular frequency. What we collect then at the detector is a signal, shown down here as the interferogram, a signal as a function of time. The Fourier transform then converts that signal as a function of time into a signal as a function of frequency. So what we're actually do to collect the infrared spectrum of our samples, we record that interferogram of our sample. Then we also have a sample or a background interferogram where we've scanned the system using the same sampling accessory, scanning parameter, keeping everything exactly the same to create two spectra that we could ratio together to get our final absorbance spectrum. The main reason we do use the microscope interferometer is that we get a very, very large increase in energy throughput, signal to noise, and wavelength accuracy that you get as compared to the older scanning infrared spectrometers. So one of the big factors, though, is how do we actually get the sample to interact with the infrared beam? And there's a wide variety of sampling techniques. Some of the classic infrared techniques used fixed path length or variable path length liquid cells, gas cells, all of which we have here. We also have a variety of specular reflectance accessories. For example, here we see a variable angle accessory that allows us to collect the reflectance off a sample at various angles. We have macroscopic ATR accessories, but the main component we use is the infrared microscope. Even beyond the infrared microscope, however, we have some extremely specialized accessories, like up here at the top of the screen, we have a technique called photoacoustic spectroscopy. We also have hyphenated accessories to go on a gas chromatograph and also to interface to our thermogravimetric analyzer. But the main instrument we use for most applications is our infrared microscope, because most of the samples we work with here are micro rather than macroscopic. So I'd like to kind of divert a little bit and talk a little bit about ATR sampling. I know a lot of people have heard about ATR, or attenuated total reflectance. It's promoted as a way of very, very simple infrared sampling. The idea is you just take your sample, push it against an ATR crystal, which is an infrared active crystal, and then you can just collect a spectrum. It's very simple preparation. You don't have to worry about thickness or anything else. However, there are some complexities in using ATR sampling. It's very much wavelength dependent. The amount of interaction between the sample is dependent upon the wavelengths. The shorter the wavelengths have less interaction. It's also dependent upon the refractive index of the crystal. It's dependent upon the refractive index of your sample, and it's dependent on the incident angle as given by this equation here, and we're not going to try to go through this whole equation. Better to just show some example of some of the problems you can run into when you just try to apply ATR sampling to every sample that comes in. Here, for example, is a spectrum. This is taken in transmission mode of a carbon black filled acrylonitrile butadiene rubber. And here we can see the classic infrared absorption, bands pointing down showing the light being absorbed. We see a general baseline offset, tilt, a little bit of curvature too, coming about from the scattering of the carbon black. So we can compare this transmission spectrum to library references, and we can very easily match up certain key spectral features. For example, the bands here very clearly matching up for a butadiene acrylonitrile polymer along with our scattering from carbon black. Now if you notice here it says carbon black, molybdisulfide, and so on. Generally those compounds only have a broad infrared scattering. They don't have a unique infrared absorption bands. This is very true for, like say, carbon black. A lot of black metal oxides, black metal sulfides, and so on will show this sort of pattern. So we can't explicitly say this baseline offset and tilt is due specifically to carbon black, but as carbon black is a very common filler in various elastomers and polymers, it's fairly good probability that it is carbon black. But let's take a look now at the spectrum of the same carbon black filled acrylonitrile butadiene rubber. And again, down here on the bottom is the spectrum collected in transmission mode. Top here is the exact same sample collected using an ATR sampling accessory. And first glance, these are both plotted in percent transmittance. I did not accidentally flip one over the other way. If you had not known that this was the carbon black-filled ABS acrylonitropbutadiene rubber, you probably would not have noticed it or realized it. You can see a lot of distortions in here. This area right here comes about from the diamond coating on the ATR. As you press a sample onto the ATR crystal, it causes various distortions, mechanical and optical distortions, so you start seeing some of these absorption bands from the diamond. What that first off causes is we lose our nitrile peak. We can't see that nitrile peak on there anymore. And identifying that very weak but very definitive nitrile band there is important in identifying this as an acrylonitrile containing compound. In addition, notice the carbon black scattering that we had seen earlier is actually severely distorted here. The ATR sampling technique is a wavelength dependent technique, so the shorter wavelengths here at the higher wave number end of the spectrum interact with the sample less, so they're scattered less by the in ATR versus the longer wavelengths. Now, depending on the carbon black loading, carbon black particle size, sometimes this baseline offset and tilt will go in a positive direction, sometimes it'll go in a negative direction, and there's been times when I've seen the tilt be completely absent and just have a general baseline offset. The third problem that we run into using ATR sampling for this sort of a sample is down here in the fingerprint region. If you notice these bands here from especially from our butadiene down here, they look like they've been derivatized. And this is actually due to an optical effect called Mee or Christensen scattering. It comes about the fact that we are having light scattered by particles whose physical size is on the same order of the wavelength of light. That, coupled with the fact that at the location of a strong absorption band, the refractive index of a material will also change. So that causes these regular absorption bands to become derivatized. So again, ATR sampling is a very promoted and can be used as a very easy, very simple sampling technique. But if you're not aware of the limitations, you can very quickly run into serious problems with that. Like I said earlier, getting back to our talk about sampling, most of what we do here is using the infrared microscope. We have a variety of sampling techniques. General infrared transparent windows, generally most often I'm using silicon windows, although we have others made out of classic potassium bromide or zinc selenide and others. For harder samples, quite often I will use the diamond anvil cell. This consists of a pair of infrared transparent diamonds. I can put a sample between, flatten it out, make it thin enough to get any infrared light through this. We could also do reflection techniques, just using a straight specular reflectance, using the same accessory. Rather than passing a beam through the sample, it would come down, reflect off the sample, and be collected again. We also have an ATR accessory for our microscope, as you see here. The very center point of that unit is a germanium ATR crystal. So we can, for microsamples, we can do ATR sampling if necessary. We don't use it that often as compared to classic transmission techniques for the reason I described as well. But in addition to our standard specular reflectance and ATR sampling, we also have a grazing angle reflectance accessory. Like the specular reflectance accessory, the light is brought down onto the sample, reflects, and comes back. Grazing angle, however, brings it in at a very, very shallow angle, so it reflects off the surface at a very shallow angle and is collected again. This would be your most useful for samples that are on a reflective substrate that are very, very thin. Under the ideal conditions, you can actually get spectra of monolayer or near monolayer organic coatings on reflective substrates like metals, elemental silicon, and the like. Main point I'm trying to make here, however, is that we do have a variety of sampling techniques for both macroscopic and microscopic analysis. There is, however, no such thing as a one-size-fits-all sampling. determining what sampling techniques to use, when it's applicable, and actually when to step back and select another or alternate sampling technique is an important factor in doing infrared analysis. So one of the big things we do here is a contamination analysis. Here's a little quick example just to bring us into this area. There's a dark fiber that was found in some packaging that we do an analysis by diamond transmission. And over here we have an infrared spectrum, absorbance spectrum with characteristic features, very broad NH-OH stretching and distinct relatively broad amide 1 and amide 2 bands here that tell us that it's a protein. Now if we go through and try to do search, it will tell us at best this is probably a protein. However, what's called the fingerprint region or in the area of proteins, side chain bands will indicate the actual kind of protein we have here. In this case it's keratin. Keratin being the most common protein or the major protein found in things like hair fibers like our last sample, skin flakes, nail fragments and so on. Has a set of distinct bands down here in the side chain or fingerprint region. But we also occasionally see, depending on what sort of samples we'll work with, other proteins come in. For example, collagen, common protein in connective tissue, muscle tissue, and so on. Characteristic band shown here, as well as albumin, the major protein in blood serum. Like I said, for most contamination cases, the protein we see most often is keratin, skin flakes, hair fragments, and so on. But occasionally we do see those others. So in terms of biomaterials, the original biomaterial I just described are proteins. You can learn a lot from infrared spectroscopy on proteins. Proteins are sensitive. The infrared absorption spectrum of proteins is sensitive to both the structure of the protein. It's also dependent a lot upon the environment in which it's in, how wet or how dry it is, ionic concentration, how it interacts with surfaces and temperature and so on. For example, here we have a whole series of protein spectra. Now these were actually collected using ATR sampling. As you hope you understand, I don't refuse to do ATR sampling. ATR is a very useful technique in the right application. But here's a series of protein spectra collected using ATR sampling over a function of different temperatures. At relatively low temperature, the protein is still in an aqueous state, still in water. And as the temperature is gradually increased, we can see the water actually start to dry out, evaporate, or disappear. And we start seeing our features from our amide 1 and 2 bands shown here. Also out in the fingerprint or side chain region, as the protein both warms up as it dries out, when it gets to the high enough temperature, it will start to denature or basically unfold. The very regular what's called the alpha helix and beta sheet structure in proteins will start to unfold to form a random form or random turns, which we can pick up and measure and characterize here by infrared spectroscopy. So besides proteins, there's a whole series of biomedical polymers that are important. We're not going to try to go over each and every biomedical polymer of importance. Just have some selected ones here. One very common polymer used in the biomedical industry is called a PBAX, also called a polyether block amide polymer. A whole range of different polymers of different hard durometers or hardness. The general hardness or durometer of these PBAX polymers is determined by the ratio of the polyether groups to the polyamide groups. And what you can see here is I have marked those key features, like in proteins, polyamides, almost exactly similar, as in a strong, distinct amide 1 and 2 bands. But then our polyether segments also give some distinct bands here at close to 1740 and 1110 wave numbers. And we can examine the ratio of the polyether absorptions to the polyamide and match it up to a rough durometer for the particular polymer. However, I will point out that durometer is a mechanical measurement. It's an ASTM standard test that describes using a particular spring-loaded plunger or spring-loaded probe of a particular geometry with a spring of a given particular force, and it measures how far it will penetrate into a sample, and that's scaled on a range of 0 to 100. Anything you add to the polymer will change its overall bulk hardness. A lot of P-BAX polymers, too, will have some inorganic fillers in there, sometimes for adding extra strength, sometimes for radioopacity. A couple common radiopacifiers here: inorganic carbonate, most likely a bismuth subcarbonate. Also, we can see classic absorption patterns here from an inorganic sulfate, most likely barium sulfate, another common radiopacifier. However, the infrared absorption is characteristic only of the molecular structure. It's not really that sensitive to the actual elemental species in a sample. So for that, we actually have the capabilities here of taking the exact same sample, perhaps that we may have run on the infrared spectrometer, and moving that over and doing elemental analysis on that exact same sample as we set up to characterize the elemental composition of that. As you see here, carbonates, sulfates, nitrates, they do show some infrared absorption, as I described earlier. Metal oxides and metal sulfides show almost no distinct mid-infrared absorption, as well as various salts, so potassium bromide, and so on. So we have the capability now of putting that either in this example here on our diamond window or another substrate and doing elemental analysis by semi-EDS directly on that sample. So here we see an example of a material that was caught up in a polymer. IR spectra of this material showed that it was a inorganic carbonate. We suspected it was calcium carbonate because calcium carbonate is a very common filler in various polymer systems. However, when we ran it on the EDS, it showed up no calcium but magnesium. It was a magnesium carbonate. Still trying to figure out how that got in there, but it was definitively shown here then that was a magnesium carbonate, while the IR showed it was a carbonate. EDS showed it was magnesium. So the two work very well together to do both molecular and elemental identification of materials, fillers, contaminants, and the like. So moving over, getting into the more complicated system, various composites and laminates, we can do single point analysis, but quite often what is of interest is not only the molecular structure and also the morphology of it. Here, for example, we have a sample of a packaging material. This is a microtome section. We can see material with a thin line of material running through that. So here we could use a combination of both the optics on the microscope, infrared microscope, along with, rather than a single point detector, we could use our infrared imager, which is a 4096 element array that's capable of collecting the infrared spectrum of every point in this area shown. So we're able to collect a spectrum from every point and then identify individual features. So for example here, on the left side we had found the features that identified that particular component as a vinyl alcohol, and we're able to plot the intensity of that vinyl alcohol as a function of position in this false color image, as well as the other major component on either side being the polypropylene. So we're able to plot the overall response of polypropylene here in these false color images, or as this pseudo 3D image here showing a band of the polyvinyl alcohol running through. The polyvinyl alcohol in this case was actually being used as an oxygen barrier in this packaging material. So polypropylene, very good, very tough material, but it is somewhat oxygen porous, so a very thin layer, in this case just a little over 10 microns of the polyvinyl alcohol serves to inhibit oxygen migration through the sample. Besides composites, quite often a lot of people get involved in adhesives and adhesive failures. We like to glue things together or fuse things together, and quite often when they don't stick, we ask why. Well, two major failures mechanisms we found in adhesion is first, some sort of a contamination at one or both surfaces, or some improper mixing and or curing of the polymer, of the adhesives. So for surface contamination, the most common, easiest way we do is some sort of a selected surface extract. Using the appropriate solvent. And the appropriate solvent, there is no one-size-fits-all solvent, just like there's no one-size-fits-all sampling accessory. Use an appropriate solvent for both the sampling substrate or materials of interest as well as the suspected contaminants. We do an extract, move that over to an infrared window, and concentrate that extract onto an infrared window. And then we can get an infrared spectrum of, in this case, a contaminant that was suspected of causing problems. The most common surface contaminant causing adhesion failure, shown right up here on the top, silicone, polydimethylsiloxane or silicone oil, very strong at inhibiting surface bonding. Others we see here as well. We run into quite often fatty acid esters from in this case, as vegetable oil, but it would also be from plant animal oils. The two next down there, oleamide, ethylene bisteramide. These two are that we affectionately refer to as bag wax. These are slip agents that are found inside common plastic bags. They're also used a lot as lubricants and mold release and so on in polymer molding, extrusion molding, and so on. So this is why we recommend the samples be not placed in plastic bags that you're going to send to us. And then down here we have non-ionic surfactants as well as other things which show up in there. So surface contamination is the major failure mechanism, but we also can examine and determine, was our adhesive properly mixed and or properly cured. One very common adhesive general class of adhesives is epoxies. Epoxies do show some very general patterns that look fairly common, but they do have some distinct bands that can be used to characterize the cure or cure state. A couple of which we've shown here. When the epoxies cure, part of the epoxy ring opening will generate an OH group. And we also start seeing a loss or a change in this epoxy ring, carbon-oxygen-carbon three-membered ring that characterize the epoxy. So if we have a specific known epoxy, we can actually create a series of known standards of the epoxy compared to the bulk material itself and do a quantitative measure of the degree of cure of the epoxy. This is kind of complementary to another technique called differential scanning calorimetry, which is also often used to determine residual uncured epoxy in an application. So I'd like to actually go into one area as well. A particular pet concern of mine is in the area of spectral interpretation. And I've encountered quite a few reports out there from other analysts, other laboratories that are doing or trying to do infrared spectroscopy. And infrared spectroscopy for identification purposes is a combined operation of all three of these operations here. First, basic interpretation of the spectrum, so-called by eye. Ideally, we'd like to compare what unknowns to perhaps some references or suspect materials, but we also compare it to our commercial reference libraries. And like I said, I've seen a lot of reports from other laboratories out there that will just give us a search report and say, well, here's the search report, here's what the search program says it is, and that's very, very uncomfortable with that sort of analysis. We do have a fairly extensive library or set of libraries, I would say, combination of both commercial libraries that we've bought from public companies, government libraries, mainly EPA libraries, and libraries we generated in-house here, where we have now well over 220,000 spectra of different chemical compounds and commercial formulations. Most of these were collected using transmission sampling. We do have a smaller subset of libraries that were collected by ATR sampling. The difficulty with those libraries, however, the ATR libraries, is that there was no information on the characteristics of the ATR sampling. And as you remember earlier, ATR sampling is very wavelength dependent. It's refractive index dependent upon the crystal. It's incident angle dependent as well. So you change those things, you can get different relative proportions of the bands at the high wave number versus the low wave number end. So we don't use the ATR libraries all that often. But in particular, I'd like to make a comment on the percent match or percent probability or hit quality index, because occasionally people will ask us to produce those sorts of numbers, and we do not provide those sorts of numbers. The software does generate those numbers, but that is not something we will provide for the reasons I'd like to explain. First off, all library spectra are typically normalized or scaled between a value of 0 to 1, 0 being no absorbance, 1 being maximum absorbance. The library spectra may be baseline corrected, interpolated, they may be ATR corrected. Very little information is provided on that. And you get libraries from different sources. They may have multiple different techniques. Plus the visualization the software does itself on the unknown. So that adds another factor of uncertainty in there. Different libraries, different sources, different processing, you're going to get different results. Besides different libraries, different processing, different initial variances, each search is not a general purpose search. Often the scientist, analyst will have to select different search windows, different search masks, in other words, telling it areas to concentrate on, telling it areas to ignore, and different search algorithms. In other words, how do we numerically compare this unknown to our library spectrum? The reason we do that is that the search algorithms, no matter what you select, can only calculate or make responses based on numerical intensities. Very strongly absorbing, very broad infrared bands will have a large influence on search results. Very weak, very sharp or narrow bands will have less of an influence. The actual absorptivity of a band will depend a lot upon the overall concentration of that material, the fundamental absorptivity of that functional group, the environment in which it's in, too. However, the absorptivity of a band is not related to how important it is in your process, in your product. A very minor contaminant may have a strong absorption. A very significant component may have a weak absorption. The search programs, no matter how sophisticated an algorithm, cannot differentiate a strongly absorbing broad band and say, well, this is not important, and say, this minor weak band is important. So here's an example of that, exactly what I'm deferring to. Spectral interpretations and search here. If we just blindly take the first hit out of here, this library search program said that our hit here was a polyacrylate coacrylonitrile, and it said it had a hit quality of 968. The particular software we use ranks everything from 0 to 999. If we round it off, let's just say this is percent quality of 96.8. Wow, it's a really high number, isn't it? However, it's actually 100% wrong. Material was identified by search as a polyacrylate coacrylonitrile. However, notice there's no nitrile band in our unknown down here. No nitrile band, therefore it cannot be an acrylonitrile. If you go, to example, to ASTM standard E2310 on automatic or a computer spectral search and identification, it quite clearly says, important and never take the first hit as being the absolute identification. You compare the spectrum of that unknown to the library and say, is this consistent? The main function of these search programs is not to identify the material, but it's to take a larger library, in our case a library of 220,000 plus compounds, and reduce it to a much smaller set of spectra, which the scientists can compare and say, is this consistent or is this not consistent, and select appropriate comparative spectra for presentation. And that is why we never present hit quality index or match quality index or say it's 96.8% probability of being this compound. For as you see, in this case, it is 100% not this compound. And with that, I'd like to say thank you very much for attending today. If you have any questions or anything, we can take those now. I'd be delighted to try to answer your questions for you, either here now or at any time. If you can have any questions you'd like to send, you can send it to our general email address here of answers@analyticalanswersinc.com. Thank you.
Thank you, Jay. That was very interesting, and I hope it dispelled some of the myths out there about polymer analysis. And we do have a question coming in. I also see some hands raised, and for those of you who joined late, I want to go over and reiterate, everybody is on mute, so rather than raising your hands, if you can submit your questions via the question functionality on the bottom right, for most people's browsers of your screen, or via chat, we will answer questions in the order in which they are received up until about 1 p.m., Jay?
About 1, that's fine, yeah.
Okay. And if you have any further questions after that, answers@analyticalanswersinc.com is the email address to submit them. But we do have a question coming in. What type of FTIR technique would you recommend to detect migration of component to surface of thin adhesive coating? And Simon is asking that question.
Okay, Simon, that's actually a good question. Like quite often here at Analytical Answers, you ask a question and we will ask a couple questions back, depending upon the adhesive coating and what it is you're looking for and how thin or how thick of a coating we're looking at, and the substrate. There's a variety of techniques we could do. In real time, for example, just thinking off the top of my head, if we were looking at, let's say, a migration of a low molecular weight solvent through the adhesive, ATR, we could place the adhesive against an ATR crystal and then monitor over time the migration of that particular component as it comes up towards the interface of the adhesive with the ATR crystal. We can monitor that as a function of time. If the adhesive is, let's say, on a polymer substrate, and it's like the example I gave earlier about the polyvinyl alcohol between the polypropylene, perhaps the molecular imaging might be useful in monitoring that migration. Another technique that has been used as well, depending on, again, the substrate and the material, a technique called photoacoustic depth profiling. I showed you the PAS, or photoacoustic sampling accessory we have up there. This rather gets into a rather involved analysis. Again, I don't know if not sure if I'm able to give you an explicit answer. It depends a lot on your adhesive, how thin or thick, and the substrate, and what it is we're looking to characterize migration, what compound or compounds we're looking to characterize migration through the adhesive. We're certainly willing to that question. An exact technique we would use would be dependent very much upon what the adhesive is, what the substrate is, and what the species or species of interest that are migrating. Okay, are you able to hear me? Okay, I've just got to report that some people may have some difficulty hearing me. My screen here shows that it is operating properly. However, okay, we apparently have gotten that corrected. So, okay, Christine is still telling me she can't hear me, but colleagues here says that they are able to hear me as well. Next question I see up here is what inspection or analysis process would you use to inspect an encapsulated electrical coil or solenoid? Interested in seeing the copper magnet wire and insulation on the wire and the potting epoxy around the wound assembly. Looking for internal voids without dissecting or cutting the assembly. That, I believe, will actually get out of the area of infrared spectroscopy. As we're looking for voids in a matrix like that, we have another technique here called X-ray microscopy. Now that's very, very good for picking up, it will certainly show the magnet wire inside a, I assume like a, yeah, they said it, an epoxy potting compound. If the epoxy potting compound has like a silica or silicate filler to give it a little more X-ray absorption, that might be useful for showing voids in a system like that. Something like that, I would certainly like to defer that to one of the other scientists here. I really have no experience other than being close to the same room as our X-ray microscope. So overall, I'm thinking right now X-ray microscopy might be the best technique, but we would probably defer that to one other scientist here. Thank you.
Okay, and I just want to remind everybody that if you do have a question that is not within the scope of this particular webinar, you can always email, again, the email address on the screen, or use the Contact Us form on the website so that you can get your question answered. We can also just, send you a response via email using the same email that you used for registration. So we have another question coming in. Recommended analyses for residues from solvent-based cleaners.
Okay. Again, assuming that the major component in the solvent, we're talking about an organic solvent, will be some organic or polymeric materials. We do that quite often using infrared spectroscopy. Essentially, especially these solvent and solvent vapor cleaning systems. A couple different ways we could do it. First, to look for what are called non-volatile residues in a cleaner. We can take an infrared substrate, typically, like I said, a silicon window, evaporate a small volume of the solvent cleaner on that window, and use the infrared microscope to collect the infrared spectrum of the non-volatile residue. That gives us a good qualitative characterization of what's in that solvent. We could also do quantitative. Quantitative actually gets a little bit outside infrared. A very, very simple way of doing quantitative analysis of non-volatile residues from the solvent cleaners is simple gravimetric analysis. We take a fixed volume of the solvent, evaporate it in a pre-weighed vessel, and just weigh the residue. Another way of doing solvent-based residues, well, solvent-based cleaners may also have other volatile compounds in there, so we also have the capability of doing gas chromatography or GC or combined GC-IR as well. although typically a volatile solvent in a solvent cleaner is less of a problem or less concern unless it starts to affect seals and gaskets and the like.
Okay, excellent. We have another question. Can you do non-destructive testing or inspection of an adhesive joint to prove that a good bond has developed?
By non-destructive, I assume you mean you don't want us to pull it apart. If it's a bond that you're able to pull apart and it's probably may or may not be a failure. We don't really do that sort of mechanical failure analysis here. I see if you've added on the additional information, a Kevlar glued to a peak polyether ether ketone, quite possibly. And is this using an epoxy or a UV cured adhesive? If we can get access to the adhesive itself, either by infrared, micro ATR sampling or reflectance. I see you've said it's a two-part epoxy. Again, we can do a infrared either ATR sampling or reflectance sampling to see is the epoxy show an infrared absorption pattern that is consistent with a properly mixed and cured epoxy. As you said, non-destructive, I'm assuming you do not want us to use a transmission sampling. To do transmission sampling of this system you described, it actually involve taking a thin slice across that bond and doing infrared transmission, either of the Kevlar epoxy peak or of the just of the sample of the epoxy. But we could do, like I said, either reflectance or ATR and compare it to a known, properly mixed and well-cured sample of that same epoxy. Again, the actual details depend a lot upon the materials and like I said, a Kevlar and peak, the size of the bond, and so on. But that's certainly possible there, yes.
Okay. We have time for one more question. I'm not seeing anything coming through in the chat, but we do have time for one more question. But we also want to remind everybody, and you will receive an invitation with a direct registration link, that we really hope you can also join us on November 15th when we'll be talking about thin film and multi-layer defect analysis in metals, metal coatings, and optical coatings. This webinar is going to focus on focused ion beam instruments and their similarities with providing high-resolution sample imaging to scanning electron microscopy, but with some differences in contrast mechanisms which can provide unique information on metallic samples. And again, that's going to be same time, lunchtime, November 15th, and that's actually going to be our last live webinar of the season. So if you've been enjoying these live webinars, you want to take part in them again, that's going to be our last one before we take a break for the holiday season, and then we'll be back again in January with some more webinars. So again, save the date, November 15th, and that's going to be another webinar that will give you a very concise and valuable, we hope, overview of a specific topic in material science. So I'm not seeing any further questions come through in the chat. Jay, do you have any final parting thoughts that you want to share as tips or caveats or just information people need to bear in mind? It was really informative and helpful to find out about bag wax and why we should not be putting our samples in plastic bags. Any further final tips for the audience?
Well, thank you very much, Christina, for hosting this. I guess my final thought on there is that I made a mention a little bit of it earlier. Infrared spectroscopy is an incredibly powerful technique. It can handle a wide range of samples and characterization. We can either do identification of bulk materials, identification of trace level contaminants, identification and quantitation of low-level additives and very low-level, anything from bulk 100% material. We've done analysis all the way down into the parts per million range. But again, depending on what it is you were looking for, the matrix we're looking into, and the species or series of species we're looking for will have a very, very strong influence on the sampling and analysis technique. It may be a simple case of just, like I said earlier, slapping it against an ATR sampling accessory and getting a spectrum. It may be involved a fairly long sample preparation, extraction, concentration, quantitative makeup, gas phase or a GC, FTIR analysis. Again, what it requires is very much dependent upon the overall analysis objectives. So with that, just want to say thank you very much for attending, and hope to hear from you soon then.
Thank you, Jay. Thank you. This was incredibly informative. Again, if you liked this webinar, please feel free to share the recording with your colleagues. If there was somebody who should have attended and wasn't available at lunchtime, a recording of this is going to go out to the same email address that you use for registration, and you will be able to access that. That will be archived indefinitely. So feel free to share it with your colleagues, as well as the next webinar, November 15th. Same time. You will be able to see all of the registration links at analyticalanswersinc.com. With that, it looks like we don't have any further questions. You can certainly follow up whether you have a need for analysis and you'd like us to help you out, or if you just have a question, answers at analyticalanswersinc.com, and Jay or one of our other scientists will be able to answer that and possibly help you out with your own thorny material sciences problems. With that, I want to thank everybody and have a great rest of the day.
Thank you.